The past few days we've talked about a covalent bond, which is when two different atoms share two electrons, and that holds them together. But those two atoms don't necessarily share the electrons 50-50. So sometimes an atom will pull the electrons more towards its side of the molecule than another side. And that's called a polar covalent bond, because what happens is the electrons get sucked towards one of the atoms, and it makes it slightly negative on that side of the molecule. So if you look at this picture of water, notice that the oxygen is very electronegative, so it's sucking all the electrons towards it, which makes that side of the molecule a little bit more negative, which means the hydrogen side is slightly more positive. So you end up with a negative pole and a positive pole, just like a north pole and a south pole, and so we call it polar covalent bonds. So again, polar means that you have a negative and a positive pole, and it's not a complete negative or positive because the electrons are not transferred, but it's just a slight negative and a slight positive, because it's kind of like it's lopsided, where the electrons hang out more on one side of the atom, or on one side of the molecule. So just in my own words, the more electronegative, and to review that term, because I know it's a big word, electronegative means that the atom has the ability to pull electrons towards it. So the more electronegative one is going to hog the shared electrons, and because the electrons spend more time on that atom, it makes it slightly negative on that side of the molecule. Versus the less electronegative atom, which doesn't get to have the electrons as much, and so it makes it slightly positive on that side. So if you look at this picture, fluorine is the most electronegative element on the periodic table, so it sucks the electrons towards the fluorine, so it's slightly negative on the fluorine side and slightly positive on the hydrogen side. So it's kind of like you have a north pole and a south pole. Nonpolar is exactly what you would think. So there is no lopsidedness, which is not a word, but that's how I think of it. There's no lopsidedness of the charge because the electrons are being shared equally. So it's a 50-50 sharing, which means that you're not going to have any slight charge on one side of it. To do this for this class, you'll see that the atoms are going to be the same kind of element. So for example, if you have chlorine and chlorine, they're both the same type of electronegativity because they're the same element. And so they're going to pull the electrons equally, which means it's going to be a 50-50 sharing. Versus if you put chlorine with hydrogen, chlorine is more electronegative, so it's going to suck it towards that side, so it's going to be slightly negative on the chlorine side. So this bottom picture is a polar molecule, this top one is a nonpolar molecule. The problem is, if you're just looking at a bond versus an entire molecule, it's two different things in terms of polarity. It is possible for a molecule to have polar bonds, but still be nonpolar overall if the molecule is symmetrical. So if you picture carbon dioxide, you have carbon in the middle, and you have an oxygen on either side of it. If you picture the carbon and the oxygen, if I'm the carbon and a professional football player is the oxygen, if it's just one carbon and one oxygen and the professional football player pulls on my arm, I'm going to tip over. So they're going to pull me over and it's going to be pulled towards the professional football player. But since this molecule also has an oxygen on the other side, it's like me standing in the middle and I have a football player on either side pulling on my arms, I'm not going to go anywhere because it's going to be completely balanced out. So even though both of the bonds in carbon dioxide are polar, so they're both getting sucked towards the oxygen, you have an oxygen on either side, so it balances out the whole molecule. So the entire thing ends up being polar. So in this class, we're only going to do simple molecules, and you can use these two criteria to help you with figuring out if they're polar or nonpolar. However, you have to keep in mind that if you do a complicated molecule, so if you take AP chemistry in the future, or if you take chemistry in college, these two rules are not going to apply because there are more complicated ones that these rules don't apply to. But for this class, we're only going to do simple molecules, and this will help you start to get the idea. So in order for a molecule to be nonpolar, it has to meet both of these requirements. If one of them is not met, it's going to make it polar. The first one is that you cannot have extra electrons on the central atom. And to be a central atom, it has to have two other things bonded to it. The other is that you have to have the same type of element all the way around the outside of the molecule. So what I want you to do is pause this video for a minute and go ahead and sketch out the Lewis dot diagrams for all 6 of these molecules. Do that now and then we'll talk about it. So hopefully you drew out those molecules, and what you should see in the first one is carbon that has a single bond to 4 of the fluorines. So the first thing is look at your carbon, and since there are no extra electrons on it, that fits the first criteria. Then look at the outside of the molecule, and all you have is fluorine, so it's the same element on the outside of the molecule. So it fits both of those criteria, which means it is nonpolar. You can label that one as nonpolar. For the pH3, you have 3 hydrogens, but the P has 2 extra dots on it if you drew it correctly, so it doesn't fit the first criteria, which automatically makes it polar. The electrons are going to get sucked towards that negative side where the 2 dots are. BF3 looks similar to pH3, except boron does not have any extra dots on it. And since it's the same element on the outside, that one is going to be nonpolar. For water, you should have 4 total dots on the oxygen, which makes that one polar. For the next one, you put carbon in the middle. You have 3 hydrogens and 1 chlorine around the carbon. So even though carbon doesn't have any extra dots, you don't have the same element on the outside because you have 3 hydrogens and 1 chlorine, so it's going to make the molecule lopsided in terms of the charge, which makes it polar. So it doesn't fit the second criteria there. And for the fluorine, there is no central atom because all you have is just 2 atoms bonded together, and since it's the same type of element, it's going to end up being nonpolar. So the problem with chemistry is that there's not a clear-cut division for a lot of the things that we teach. So to make something ionic versus covalent, there's kind of a spectrum where it goes on a continuum, and it's based on how equally the electrons are shared. So if you picture 2 atoms that have the same electronegativity, they're going to share the electrons exactly equally, and that's called nonpolar. If one of those 2 atoms is slightly electronegative, slightly more electronegative, they're still going to share it, but they share it unevenly, and that's called polar covalent. And if one of the atoms is really electronegative and the other one is not, so the difference is really big, then it's going to get transferred completely, which is called ionic. So here's the scale. This is the difference in electronegativity. So if the difference in electronegativity is 0, which is down here on the scale, it's going to be nonpolar covalent. So they're going to share it 50-50, equal sharing of electrons. Once the difference gets up to about 0.4, they switch it over to be polar covalent. So this range right here between the 0.4 and the 1.7, if the difference in electronegativity is between those 2 numbers, it's going to be polar covalent. And if the difference is greater than 1.7, so that means there's a huge difference in electronegativity, the electrons get completely transferred, and that makes it ionic. So just to review this word again, I know it's been another chapter since we've talked about it, so don't forget that electronegativity is the ability to attract electrons, and atoms with a large electronegativity will be able to attract the electrons easier. The trend for this, to review from the periodic table chapter, is that as you go up on the periodic table, the electronegativity also increases. And as you go to the right, the electronegativity increases, but don't forget that the noble gases have an electronegativity of 0 because they're already stable, so they're never going to attract the electrons. So this is a chart that shows the electronegativity values of different elements. So what you would have to do for possibly a test or a quiz is I would give you these values and ask you about different bonds. For example, if you look at the next slide, Na versus Cl, let me go back to the previous one. So sodium is 0.9 and chlorine is 3. So the difference between those is 2.1, which falls into the category. Let me go back to this one. It's alright, we'll just go, you can look in your notes. It falls into the category of ionic. So 2.1 is greater than 1.7, which would be an ionic bond. If you look at fluorine, it doesn't even matter what the value is. It happens to be 4, but because they're both 4, the difference between them would be 0, because it would be 4 minus 4. So therefore, this one's going to be nonpolar because they're going to share it evenly. For carbon and hydrogen, carbon is 2.5, hydrogen is 2.1. So the difference between those is right around the cutoff between polar and nonpolar. It's kind of polar, but it's kind of nonpolar. And I wouldn't give you one like that on the test, so I would give you one that's a clear-cut division. If you look at carbon and sulfur, they're actually both 2.5, so even though they're different elements, the difference between them is 0, which is going to make it nonpolar. And you should be able to look up the last 3, look up the numbers, subtract them, and see where they fall into that range. And you should figure out that MgBr, I think it was polar, let's see. Magnesium is 1.2, bromine is 2.8. So the difference between those is 1.6, which makes it polar. It's almost ionic, but it falls within the polar range. And NO, let's see, N versus O, nitrogen is 3, oxygen is 3.5. So that one's also going to be polar, but this time it's only barely polar. It's almost nonpolar. And KCl you should get is going to be an ionic compound. So the reason you need to know this is if I give you a list of compounds and I say which one has the highest melting point, well obviously you're not going to memorize the melting points of a whole bunch of different compounds, so you need to be able to compare the compounds based on their bonding. So once you determine that one is ionic, you know it's going to have the highest melting point and the highest boiling point. That's what MP and BP stand for. If you determine that one is nonpolar covalent, that's going to be a low melting point and a low boiling point. So using the types of bonds, you can compare different compounds in terms of how well you can break them apart. So it takes a lot of energy to pull apart ionic compounds because they have the strongest bonds. Worksheet number 5 will allow you to practice polarity. So if you haven't done worksheet 5, go ahead and try some of the problems on that worksheet, and we will go over those tomorrow. That's all for today.